Every smart contract on Ethereum that uses role-based access control has a dirty secret. Everyone can see who has what role. Your admin address, for example, public. Your list of approved traders, public. Addresses as well. Which wallets have LP privileges? Completely, permanently public. And that's not a bug. That's how it was designed. OpenZeppelin access control on Ethereum stores roles in a public meeting. Anyone can call hasRole, pass in an address, and instantly know whether that person is an admin, a minter, a poser, whatever role you've defined. Now imagine doing the same thing, role-based access control, but where nobody can see who has which role. You can prove you have the role, but you just can't prove it about someone else. And nobody's watching the chain can figure that either. So that's what OpenZeppelin built for Midnight. And the way they did it, it's a masterclass in CK design patterns. Okay, let's start with what we know. Ethereum's access control, the OpenZeppelin version that secured billions of dollars in DeFi, it's roughly 60 lines of solidity. And it's elegant. We've got a mapping, roles, key by role hash pointing to another mapping of addresses to booleans. When you call grantRole, for example, it flips a boolean to true. When you call hasRole, it reads that boolean. When you call revoke role, it flips it back to false. Simple, battle tested, it's being audited to death. But here's the thing. That mapping is public storage. Every role grant emits a role granted event with that account address and role hash right there in a event log in Ethereum. Anyone running an indexer, for example, or just looking at Etherscan, you can actually create a picture of the access control in seconds of that smart contract. For a lot of applications, that's fine, maybe even desirable. Transparency is the point of the public blockchains. But think about, for example, a compliance system where knowing who the compliance officers are creates maybe a social engineering attack vector, or a DAO where knowing who holds governance roles lets people target them with bribes, for example. Or a DeFi protocol where knowing which addresses are whitelisted LPs, for sure it's gonna give competitors intelligence about the liquidity strategy. In these cases, public permissions aren't just inconvenient, they are a security liability. So how do you build the same access control system, same roles, same checks, same composability, but where the role assignments are cryptographically hidden? This is where Midnight's AccessControl.compact comes in. Same concept, completely different architecture. Instead of 60 lines of code and a public mapping, you're looking now at approx 200 plus lines of compact and 3 pieces of ledger state that work together. First, a Merkle tree. This is where role commitments live. Depth 10, what that means? It means that it can hold up to 1024 entries. Each entry is a 32-byte hash, a commitment that some user has some role. But the hash doesn't tell you which user or which role. It's a one-way function. You can't reverse it. Second, a set for nullifiers. This prevents the same role, for example, from being granted twice to the same user. Every time a role is granted, a unique nullifier is computed and added to the set. If someone tries to grant the same role again, the nullifier will already exist and the transaction is gonna fail. Third, a counter for the index. This tracks the next insertion position in the Merkle tree. Simple bookkeeping, but essential for the tree structure. The roles themselves are defined as an enum: admin, LP, trader, none, clean, and explicit. Now, here's the mental model that makes this click. On Ethereum, role storage is a lookup table. You ask, does this address have this role? And you read the answer directly from the storage. On Midnight, on the other hand, role storage is a commitment scheme. You ask, can I prove this address has this role? And you provide a cryptographic proof that that commitment exists in the tree without revealing the commitment contains. Same question, fundamentally different trust model. Okay, let's trace through grantRole step by step, because this is where the CK magic lives. Step 1. You compute the commitment. The function calls hasUserRole, which takes the user public key and the role and produces a persistent hash. This is a collision-resistant hash that commits to the user role pair. The output is a 32-byte value that's deterministic. What that means? Same input always produce the same hash, but it is irreversible. You can't look at the hash and figure out the user or the role. Step 2. Nullifier generation. This is critical. The circuit calls witness getCircuitKey, a witness function that provides a secret key from off-chain private state. The secret key is combined with the commitment to produce a nullifier. And here's the key insight. The secret key enters the circuit through the witness and participates in the computation, but never gets written to the ledger. It exists inside the CK proof and nowhere else on chain. Step 3. Duplicate check. The circuit checks that this nullifier doesn't already exist in the role nullifier set. If it does, someone already granted this exact role to this exact user, and the transaction reverts. This prevents double granting without anyone knowing what was granted. Step 4. Merkle tree insertion. The commitment gets inserted into the role commits tree at the current index position. The index counter increments. Step 5. Private state update. The circuit calls witness update role, which tells the off-chain witness to start the new role assignment in its local private state. This is where the user's role mapping actually lives, not on chain, but in the witness. Now, and this is a little bit subtle, the contract uses this clause on both the nullifier and the commitment before they go on chain. Disclosure means these values becomes part of the public transaction data, but that's fine. The nullifier is derived from a secret key nobody else has. The commitment is a hash nobody can reverse. Making them public doesn't leak the private input. It just makes the Merkle tree and nullifier set verifiable by anyone. Granting roles, it's one half. Verifying them, it's the other. And hasRole is where Merkle proof do their thing. Here's the flow. First, the circuit computes hash user role again. Same user, same role, same deterministic hash. This gives you the expected leaf value. Then it calls the witness getRole Merkle path, passing it in the commitment. This witness function looks up the commitment in the off-chain private state and returns a maybe Merkle tree path. If the role was granted, you get sum with a full Merkle path, the sequence of siblings hashes from the leaf up to the root. If the role was never granted, you get none. If the path exists, the circuit runs two checks. First, check roots. It takes the on-chain Merkle tree and the provided path and verifies that walking the path from the leaf produces the same roots that's stored on-chain. This confirms the path is legitimate and corresponds to an actual entry in the tree. Second, it verifies the leaf at the path matches the commitment you computed. This confirms that the specific user role pair you are checking it's the one that's positioned in the tree. If both check passes, that means the user has a role. If either fails, that means it's the wrong path, wrong leaf, and no path at all. The check fails. Okay, and the beautiful part is that the circuit never sees the full Merkle tree. It only sees the path, a logarithmic slice. The verifier on chain only sees the proof that this computation was done correctly. Nobody learns which leaf position was checked. Nobody learns which role was verified. They just learned, yes, this proof is valid, and the user is authorized. Let's draw the line clearly, because understanding what's public and what's private is everything in CK system. On chain, visible to everyone, the Merkle tree structure, including the root hash, the nullifier set, the commitment hashes stored in the tree, the fact that some role was granted to someone, the counter tracking how many roles have been granted. Now, off-chain, private to the user, which user holds which role, the secret key used for nullifier generation, the Merkle path that prove membership, the actual mapping from users to roles, the enum values, admin, LPs, traders behind each commitment. The disclosed function is the boundary marker. When the contract calls disclose on a value, it's explicitly saying this value will be part of the public transaction. Everything else is going to stay inside the CK circuit. The role user identity and role enum enter the circuit as private inputs, get hashed into commitments, and only the commitments cross that disclosure boundary. This is what makes the system work. An observer sees that a Merkle tree grew by one entry. They see a new nullifier in the set. They can even verify that the commitment and nullifier are well formed, but they cannot determine which user was granted which role. The hash is a one-way wall. Compare that to Ethereum, where role-granted roles, account senders, for example, broadcast the complete picture to every node on the network. The witness function are the heroes of this contract, and they represent a pattern you'll see in every serious midnight application. 3 witnesses power the access control contract. Witness gets secret key, returns a secret key that exists only in the user's local environment. This key is used to compute nullifiers. It enters the CK circuit as a private input, participates in the hash computation, and vanishes. The proof attests that the computation was done correctly, but then the key itself is never revealed. This is the core CK pattern. Prove you know a value without showing the value. Another function, witness update role. When a new role is granted, this witness stores the mapping locally. It's the off-chain database of who has what. The on-chain Merkle tree stores commitments, but only the witness knows which commitment maps to which user role pair. Another function, the witness get role Merkle path. When you need to prove a role, this witness retrieves the Merkle path for a given commitment. It returns a maybe type with some path if the role exists and none if it doesn't. The circuit uses this path to verify membership against the on-chain roots. The pattern here is compute off-chain, proof on-chain. The witness handles the actual state. They know the users, the roles, the path. The circuit handles the verification. It checks the math, generates the proof, and discloses only what's necessary. This separation is what gives Midnight its privacy guarantees. The ledger holds commitments, the witness holds the truth. And the CK proof bridges the two without leaking the private side. This pattern, Merkle commitments plus nullifiers for access control, unlocks a lot of use cases that are simply impossible on transparent chains. Compliance roles, think regulated DeFi. A protocol needs certain addresses to be KYC verified before they can trade. On Ethereum, that KYC what list is public. Everyone knows which addresses passed compliance. On midnight, you prove you are on the list without revealing your address to other participants. The compliance officer can verify, other traders cannot. DAO governance, for example. Voting eligibility based on token holdings or delegation, today that's all on chain. With CK access control, a DAO member can prove they are eligible to vote without revealing how many tokens they hold or who delegated to them. This skill allows us to have avoid vote buying, because you can't verify how someone voted if you can't even verify they were eligible. DeFi LP access tiers, another use case. Protocols offer different fee tiers or pool access based on LP status. With this pattern, an LP proves they qualify for a tier without exposing their position size to competitors. LunarSwap, the DEX that OpenZeppelin built, use this exact access control module, uses this LP and trader roles. The underlying insight is the same in every case. Prove membership in a set without revealing which member you are. That's what the Merkle tree plus the nullifier pattern gives you. And because OpenZeppelin built it as a composable module with export, any compact contract can import it now and get the CK native role-based access control out of the box. Well, more code for less transparency. 200 lines instead of 60. But that trade-off kind of buys you something Ethereum fundamentally cannot offer: permissions that are verifiable without being visible. If you want to see how this access control module plugs into a real application, the build session walks through the full LunarSwap DEX architecture, contracts, wallet integration, and how the roles actually wire into a swap logic. And the explainer covers why OpenZeppelin building for midnight matters for the whole ecosystem. We help teams build exactly this: privacy-preserving smart contract systems with smart compliance built in. Links to everything in the description below, including how to work with us. And if you want direct async access to the team for your specific questions, check out our membership. Post your questions in the shared cohort room. Get expert answers. It's the fastest way to get unstuck while you're building. Link below. See you in the next one.